Hello again, and welcome to our lecture on basic integration rules. This is a very big topic in calculus, how to find antiderivatives, how to integrate functions. We've seen in the last few lectures that the applications of integration lead to complicated integrals, and solving those integrals is big business. It can be very, very difficult. When I was a student in taking calculus, we didn't have computers or graphing calculators available, and we had to do all these integrals by hand. It was very, very difficult, and we studied integration techniques for weeks and weeks and weeks. That seems to be dying off now as technology comes into play, especially in the advanced placement program, where integration techniques play a much smaller role than, say, in a university calculus course. So what I'd like to do in today's lecture and the next lecture is talk about some more techniques for finding antiderivatives. We know how to do substitution and to apply those to various examples. But now we're going to look a little bit closer at that substitution rule and also pull together our list of formulas that we know so far. In the following lecture, I'd like to spend some time on a technique called integration by parts and also look at some trigonometric integrals, but that will be the following lecture. So let's step back and start making a list of the integration formulas that we've learned to love in this course so far. There was this power rule, the integral of x to the n dx, and that of course is you raise the exponent to n plus 1 and divide by what you raised it to, n plus 1, and in all these formulas there's plus an arbitrary constant. And remember, in this formula n cannot be minus 1. And so what did we do with the integral of 1 over x, the missing case? Well, we defined the logarithm function, the natural logarithmic function, to fill the gap. So the antiderivative of 1 over x is log of the absolute value of x. That's to make sure that x is never negative. Good. The inverse of the log function was the exponential function e to the x, and it had a wonderful set of formulas. The derivative of e to the x was itself, and so the antiderivative of e to the x is e to the x plus your constant. And then we took a little turn to a more complicated situation where you had a to the x, where a was some other positive constant different than e, and now the formula was 1 over log a times a to the x plus c. Good. Then we developed the antiderivatives of the trigonometric functions. Let's step through those again. The integral of sine is, of course, minus the cosine plus a constant. Why? Because the derivative of cosine is minus the sine, so we have that unfortunate minus sign situation here. The antiderivative of cosine, of course, is sine x plus a constant. What about tangent? You remember we needed logarithms to solve that problem. We wrote it as sine over cosine, and the answer was minus log absolute value of cosine plus a constant, and that also can be written as log of the absolute value of the secant function plus a constant. And cotangent would be similar to tangent, and that's log of the absolute value of sine x plus a constant. I think I mentioned the integral of secant as kind of a funny looking formula, kind of complicated. It turned out to be log of the absolute value of secant plus tangent plus a constant. Cosecant turns out to be just as difficult. It's minus the logarithm of the absolute value of cosecant plus cotangent. I would not memorize that cosecant formula, but most of my students learn the secant integral because it comes up a little bit more. Then we have some antiderivatives that come directly from different derivative formulas. For example, the derivative of tangent is secant squared. That means that the antiderivative of secant squared is tangent plus a constant. In the same vein, the derivative of secant is secant tangent. So the antiderivative of secant tangent is secant plus a constant. So those just they come for free because we know derivative formulas. Well, then we studied inverse trigonometric functions. That was a complicated lecture, had a lot of pre-calculus in it, and we developed derivative formulas for the inverse trig functions, and that gave rise to integral formulas. And we observed something kind of amazing, that the formulas here for the derivatives of the inverse trig functions did not involve trigonometry. And then the integral formulas go something like this. The integral of 1 over the square root of a squared minus x squared. A here is a positive constant. That turns out to be arc sine of x over a plus your constant. You can check that by differentiating arc sine of x over a. Here's another useful formula. The antiderivative of 1 over a squared plus x squared is 1 over a arc tangent of x over a plus a constant. And then the antiderivative of 1 over x square roots x squared minus a squared, kind of a complicated integrand. That turns out to be 1 over a arc secant absolute value of x over a. Ouch. Ouch. Couple of comments here. One is the plus constant, plus c. I always forget to put plus c when I'm writing things down, and my students forget it a lot too. Some teachers are really mean. If you forget to write down the plus c, they take off a lot of points. I'm a little kinder there because it gets tedious to keep saying plus c, plus c, plus c. Another comment here, that arc secant formula we just looked at. Remember that there's a lot of discussion as to what the definition of the arc secant function really is. That's a tough formula. Don't memorize it. In fact, if you should ask your teacher which formulas you are expected to memorize. In a college course, this always happens. The teacher will say, I want you to know blah, 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 blah. And sometimes they're really nice and they give you a formula sheet with all the formulas you need to know. So you need to ask your teacher which formulas you should memorize. Let's do some examples now with these formulas to get comfortable with applying our list of integration formulas to some typical integrals. How about 4 over the quantity x squared plus 9? What's its antiderivative? Well, this fits the form of the arctangent formula, 1 over a squared plus x squared. In this case, a is 3, because 3 squared is 9. The 4 can come outside the integral sign, so I'm left with 4 times 1 over x squared plus 3 squared. That's precisely the form of the formula, so the answer is 4 times 1/3 arctangent x over 3 plus a constant. Good. Here's a problem that looks pretty much like the one we just did. Instead of 4 in the numerator, now I have 4x in the numerator. Let's see what happens now. What's the antiderivative of 4x over x squared plus 9? Well, I hope you recognize this one is actually a substitution problem. You would let u be x squared plus 9, and then du is 2x. And I've got 4x there, so I take 2 and move it outside and leaving 2x inside. And now I have the precise form of the logarithm rule, 1 over u du. And so the answer is 2, that 2 is the one that's outside, natural log of the absolute value of x squared plus 9, plus a constant. And now you don't need the absolute value signs, do you? Because x squared plus 9 is positive, so you could write it as 2 log quantity x squared plus 9 plus your constant. And in fact, you could really be fancy and move the 2 in front up to be an exponent. And another way of writing the answer is log of the quantity x squared plus 9 squared plus a constant. So lots of different forms. All of them are correct. And of course, in the back of your textbook, they might show one of these forms. You shouldn't panic if you have a different form of the answer. You're also correct. They just wrote it differently. Okay, let's change it one more time. Now let's make the numerator 4x squared. over x squared plus 9. So again, this kind of looks like the previous two problems. What happens here? Well, here we need to do long division. We have to divide the denominator into the numerator. And if you do that, you get the following. 4 minus the quantity 36 over x squared plus 9. Let's check to see if I did it correctly. Take 4 minus 36 over x squared plus 9 and make a common denominator. What do you get? You get 4x squared plus 36 minus 36, and you're back to where you started from. So the long division was done correctly. And now I have two integrals. I have the integral of 4 dx minus 36 times the integral of 1 over x squared plus 9. Or if you want, x squared plus 3 squared. Okay, how about that first integral? That's pretty easy. That's just 4x. How about that second one? Oh, that's an arctangent again, isn't it? So the second one will be minus 36 times 1/3 arctangent x over 3 plus a constant. And if you want, you could multiply it out to get 4x minus 12 arctangent x over 3 plus a constant. So kind of interesting that those three examples almost looked alike. My eyes almost fooled me. You had to pay real attention to the numerator. And the answers were very, very different in each case. The second one, in fact, was a logarithm rule. The third one needed long division, a tough pre-calculus topic. I might have mentioned this earlier, but a lot of my students come to my course at the University of Florida, and they never studied long division in the public schools or the private schools. And when I say the word long division, they go, what's that? You know, gulp. It turns out you still need long division in a lot of college calculus courses. Okay, I'd like to now look at an area problem that has a very interesting feature that will be important in applied mathematics when you're doing numerical integration. So the problem kind of starts off fairly easily. We're going to find the area bounded by the curve x plus 3 over the square root of 4 minus x squared between 0 and 1. Here's a picture of that area. I've drawn the curve, and I'm going from 0 to 1. It's that shaded region that I'm going to calculate. Good. It's a little bit complicated, it looks like, but I'm going to split this into two integrals. The first one is 0 to 1 x over square root of 4 minus x squared. And the second one is 3 over the square root of 4 minus x squared. So let's savor that first one for a moment. What do we got here? Well, the square root's in the denominator. So if I push it up to the numerator, it's 4 minus x squared to the minus 1/2 power. And that's going to be substitution, letting u be 4 minus x squared, so du is minus 2x. And I've got the x there, don't I? It's just the minus 2 I don't have. So I multiply by minus 2 inside the parentheses, and I multiply by minus 1/2 outside so I don't change the problem. How about the second one? Well, the second one, I can move the 3 outside the integral sign, and I have 0 to 1, 1 over the square root, and 4 is, of course, 2 squared, so it's 2 squared minus x squared. I recognize that as an arc sign. Good. Let's keep going. We now anti-differentiate the first one. We get 4 minus x squared to the 1/2 power divided by 1/2, and that cancels with the 1/2 out front, and we're left just with minus 4 minus x squared to the 1/2 power. And the second one, as I said earlier, is arc sine x over 2 times the 3 that's sitting out in front of the integral sign. Okay, that was a lot of work, some heavy lifting there. Now we have to plug in the endpoints, and this too is interesting, I think. Let's plug in 1, the top endpoint. What do I get? I get 4 minus 1, which is 3 square rooted, so I get minus square root of 3. And now here's one that's more difficult. I plug in 1 into 3 arc sine x over 2. So I get 3 arc sine 1/2. So what's the arc sine of 1/2, I asked you? Well, let's see. Arc sine of 1/2, I'm looking for a number whose sine is 1/2. And I'm in the proper restricted domain. And that angle is pi over 6, because sine of pi over 6 is 1/2. So arc sine of 1/2 is pi over 6. Pretty tough pre-calculus, I admit. So we have 3 times pi over 6 for that piece. And now we put the 0 in, and we get 4 minus 0 to the 1/2, which is 2. So it's minus the quantity minus 2. And of course, arc sine of 0 is 0. And that all simplifies to about 1.839. Good. A lot of work, but it had some interesting pre-calculus, I thought. So there's the picture of the problem again. I want you to imagine, though, that I increase the area. Let's not go from 0 to 1, but how about up to 1.99? You might notice that in this graph, when x is 2, the denominator is not defined. Well, the denominator is 0, so the function's not defined. It has a vertical asymptote at x equals 2 because we're dividing by 0 there. That's why in the graph I have that dotted vertical line. So now I'm going to do the area right up hugging the vertical asymptote. Let's calculate it from 0 to 1.99, the same function. Would that be difficult to do by hand, just like we did the previous problem? I say no. And here's why I say that. It's the same antiderivative. The only difficulty is, instead of plugging in 1 as your upper limit of integration, you're going to now have to plug in 1.99. But that's not so bad. It's just a messy decimal. So it wouldn't be difficult by hand to do that problem with the limit being 1.99. But it's really curious. When I put this into a computer program to calculate that integral, I got an answer that was not very accurate. The exact answer, doing it by hand, is approximately 6.213. But my computer gave me 6.889. Isn't that strange? That's a bad answer. You don't want to build a bridge based on these kinds of computations because you're way off. And in fact, if you went to 1.999, it would be even worse. Now, think of why that might be true. Imagine the trapezoid rule in this picture. You're forming trapezoids, but now these trapezoids are very, very vertical. The top is getting very vertical, isn't it? And the computer struggles with that, adding up the areas of those trapezoids. That's why when you get close to a vertical asymptote, computers will have trouble with numerical integration. You've got to be careful about that. Good. You know, when I took calculus, my professors always seemed like they were really, really smart because they could do integrals that I had no idea how to even begin. And let me show you one, just sort of to show you some of the art form involved. I'm going to show you an interesting integral, and we'll find an antiderivative. And then I'll again mention some technology issues with this problem. So I'm going to try to find the antiderivative of 1 over 1 minus sine x. And if you're like me, hopefully a normal human being, you look at that and go, I have no idea how to attack that problem. I don't know what to do. By the way, don't do what some people would want to do, and that is split it up into 1 over 1 minus 1 over sine x. You can't split denominators. You can only split numerators. So what do? Well, here's a clever little trick. Multiply numerator and denominator by 1 plus sine x divided by 1 plus sine x. I like to think of that sort of as multiplying by the conjugate. And you'll see what happens in a moment. So the numerator becomes 1 plus sine x, and the denominator is 1 minus sine squared, because 1 minus sine x times 1 plus sine x is the difference of two squares, 1 minus sine squared. But our fundamental trig identity says that 1 minus sine squared is cosine squared. So now I have a new integral, And this one I can split up. I can split the numerator. That was the reason for doing the trick. And I get 1 over cosine squared as my first integral, and the second one will be sine over cosine squared. Good. Can we do those problems? Well, what's 1 over cosine squared? Well, it goes by the other name of secant squared. Good. And the second one, think of it this way. Think of sine over cosine squared as 1 over cosine times sine over cosine. And 1 over cosine is secant, and and sine over cosine is tangent. So we get that we have two integrals to solve, the integral of secant squared and the integral of secant tangent. Well, I know the answer. The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent, and the second one is secant. So here's our final answer. Tangent x plus secant x plus an arbitrary constant. Wasn't that clever? I never would have thought of that, except I prepared my lecture ahead of time. It's almost an art form. It's amazing. A lot of it is experience. I've seen professors who can do almost any integral you can imagine because they have a tremendous amount of experience in solving such problems. Let me say a little bit more about this example. The answer we got was tangent x plus secant x plus a constant. Well, I own a fancy calculator that can do integrals. It can find antiderivatives for lots of functions. Not every function, but for lots. So I put it into my calculator, and I got a different answer. Gulp. I got the answer minus cosine x over sine x minus 1 plus a constant. And now, wait a minute. We have two answers here. Trust me, these are equivalent to each other. These two answers are both correct. They actually differ by a constant. I invite you to try to show that these two answers are actually equivalent to each other. Both of them are correct. It's kind of interesting that my calculator gave me one form of the answer, and when I did it by hand, I got a different form. Okay, let me talk to you with some fatherly advice now about studying calculus. You've got to practice calculus. This is not a spectator sport. I like to tell my students that if you want to be a good basketball player, you don't just watch other players shoot free throws. You have to go out there yourself and shoot those free throws. In particular, I think it's important in math courses to write out the problems as you're solving them. It's one thing to kind of look at the professor who's doing it and you're sort of going, oh yeah, nice move. Oh yeah, great step, professor, you're doing okay. It's better if you write it out yourself. A lot of learning goes from the pencil through the arm and up to the brain. Here's something else I tell my students to do. I almost insist upon it, that they rewrite their notes. So when you take a class, any math class, or actually any class, rewrite your lecture notes after the class. I've noticed the following. Students will come into my office and they'll have a question about something. Professor, how do you do this problem? And I go, well, I did a problem just like that in lecture. Show me your notes and I'll show you where I did it. And they open up their notebook and it's just garbage in there. I don't know what they wrote down. It must have been a different professor or something because they didn't rewrite their notes. The advantage of rewriting is you learn the material. You really get to get it through your arm. And second of all, 5 years later, if you have to go back and look at your calculus material, you'll have a set of very clean, clear notes to work from. Okay, enough fatherly advice. Let's go back and point out something a little more mundane. I mentioned this earlier. One of the most common errors I see in algebra is the error of splitting up a fraction, splitting up the denominator of a fraction. In other words, 1 over 1 minus sine x is not 1 over 1 minus 1 over sine x. You can only split up numerators as we did in the last example. Good. Let's now turn to an arc length problem. We've been doing, we did arc length last lecture. I'd like to look at a fairly simple example of an arc length problem and show you an integration technique that comes into play. So let's find the arc length of log cosine x between 0 and pi over 3. Here's a picture of that curve. And we're trying to find the length of that curve starting at 0, 0 and ending when x is pi over 3. So remember how we do this. The curve is log cosine x. We take its derivative. Log of something is 1 over the thing, 1 over cosine, times the derivative of cosine, which is minus the sine. So the derivative is minus tangent x. Then I form 1 plus the derivative squared. That's 1 plus tangent squared. Tangent squared plus 1 is secant squared by a trigonometric identity. So that's pretty nice. And so my arc length formula is the integral from a to b square root 1 plus the derivative squared. And in our case, it's 0 to pi over 3, the square root of secant squared, which of course is just secant. What's the antiderivative of secant? That was on our formula list a few minutes ago. It's the natural log of the absolute value secant plus tangent. And if you plug in the endpoints pi over 3 and 0, you get the following. Well, secant of pi over 3, what's that? Well, what's the cosine of pi over 3? That's a half. So the secant of pi over 3 is 2. How about the tangent of pi over 3? That's easier. That's the square root of 3. So the first term is log quantity 2 plus root 3. And the second term, when you plug in 0, secant of 0 is 1, tangent 0 is 0, log of 1 is 0. So our answer is about 1.317. Good. That was kind of a nice problem in that we saw a trig identity coming into play. Notice it sort of reflects the issue that we had to have a fairly complicated function to give rise to an integral that we actually could solve. Now, suppose you change that function not to log cosine, but rather just cosine, much simpler. In other words, what's the length of a piece of the cosine curve? That should be fairly simple, shouldn't it? The cosine length. What's the length of a piece of the cosine? Well, it turns out that gives rise to the square root of 1 plus sine squared. Why is that? The derivative of cosine is minus the sine. So 1 plus the derivative squared is 1 plus minus sine x quantity squared. And that doesn't simplify, does it? That's so sad. 1 plus sine squared x does not have a trig formula to compactify it. And you're left with that radical. And in fact, you have to use a numerical technique. When I took out my fancy calculator that can find antiderivatives, I told you I had that fancy calculator. When I put this one in, what's the antiderivative of the square root of 1 plus sine squared x? You know what it did? It just gave me back the same problem, kind of telling me I can't do it. The calculator can't find the antiderivative because there isn't one among the elementary functions. So you have to use a numerical technique here. You would have to use something like the trapezoid rule. Good. I think we've covered a lot of material today, most of which was, I'd like to say, review of material we covered all through this course. We used our derivative formulas to generate some integral formulas, and then we put together other integral formulas coming from the inverse trigonometric functions, the power rule, etc. So we have this giant list of integration formulas. And I'm sure you agree with me that integration is difficult. It's harder than differentiation. That's the way it is. Sorry about that. As I said earlier, in the advanced placement program, there is less and less emphasis on integration, whereas in college, it still is a very important topic. Next time, we'll spend some more time looking at some integration techniques. We'll do something called the integration by parts. and that's based on the product rule for derivatives, and we'll look a bit at some integrals involving trigonometric functions. I think you'll enjoy it, and I look forward to seeing you next time. Thank you.